Hey students, welcome back. This is our next video. This time we're actually going to be calculating equilibrium concentrations from some data that is given to us. So you'll definitely want a calculator for this. And let's just kind of jump in because we're also going to introduce ice charts today. So let's see what we've got. So this is 16.6 if you want to read more about it. I've actually kind of followed the book pretty closely here. We're still going to be using the law of mass action there. So let's kind of just jump right in. So we can use the law of mass action to calculate our equilibrium concentrations. Now, here's something we need to remember. So our equilibrium constant will always stay the same, right? It's a constant, right? So it doesn't matter where we start, and we'll actually do a little work with that later, talking about where we start and how it'll end, but it'll always end, and when I say end, it'll reach equilibrium at the same ratio of products to reactants no matter where we start. Okay? Kind of moving on here, we're going to use our ice charts to figure these things out. And ice charts, if you've never seen them before, are actually pretty handy. Some people use them for stoichiometry, but I only use them for equilibrium because to me, we only want to keep one little hint for each topic. So I stands for initial. This is our initial concentration. All right, this is what we started with. This is what will tell us at the beginning of the reaction, it was this much. C stands for our change in concentration. All right, and this is based on stoichiometry, and we'll see that in our example down below, but it is based on stoichiometry, so we have to do a little stoichiometry there. If 1 mole is used of one reactant, but we have 2 of the other one, we'll have to do 2. All right, but we'll get there. It'll make more sense once we kind of see it. Next up, our last one, E is our equilibrium concentration. So this is kind of just like putting these two guys together and subtracting them. So these are our equilibrium concentrations, and that is what we can then put into our Kc, right? So we can transfer that to our Kc, or our equilibrium constant expression, when we're ready for that. So let's see if we just can't work a couple of examples here and kind of see if it makes sense for us there. All right, so trying to make it a little bigger. Consider the following reaction. We have carbon monoxide plus 2 hydrogen gases gives us methanol there. And what we've got is, it says a reaction mixture initially contains that and that. Then at equilibrium, we know our concentration of CO is at 0.10, and we're trying to find our equilibrium constant. So we're trying to find K. All right, so here's how I like to start. I always like to start by putting our balanced chemical equation first, right? And I'm going to leave my state symbols on there for right now. And yes, I know we have it above, but it'll make it easier to put my ice chart down below it here. And it looks like I forgot to put my little gas on there, but that'll work. Okay, and so now we're going to put our ice chart down below it. Remember, I stands for our initial concentration. So in our problem, it tells us we have 0.500 molar of CO, and we have 1.00 molar of H2. It says nothing about CH3, and since it's the beginning of a reaction, we're going to go ahead and assume 0 right here. We have 0 CH3OH. Now, at equilibrium, we know we have 0.15 moles of CO, molar CO. And what we're going to do there is just do a little bit of work. So if we look at our change, right? In our change, our reactants are going to be going down. So we're going to subtract our reactants, and then we'll add products. So let's look at that in terms of just kind of using an x. So minus 1x, because there's a 1 understood to be out in front of that CO, right? Then we're going to say minus 2x, because there's twice as much H2 used up as CO. And then last but not least, we're going to add, since it's a product, we're going to add 1x of CH3OH. All right? From here, it becomes a little kind of like problem solving it out. So 0.5 minus x gives me 0.15. So 0.5 minus 0.15, and that will tell me what my x is, right? So my x is going to be 0.35. Is everybody okay with that? We understand how we got 0.35. So instead of these x's right here, I'm going to take this x out and that 1, and I'm going to say minus 0.35. So now 2 times 0.35. Right? And this one is just going to be 1 times 0.35. Right? So for my equilibrium concentrations, we've got 1 minus 0.7 when we do our math, right? Which is 0.30, right? And that's molar. And then we've got 0.35 molar there for our answer. All right? Everybody doing okay with that so far? Okay? I'm going to erase this x equals 0.35 just so I'm not confused. All right? Now, kind of shifting gears just a little bit. Now we can write our equilibrium constant expression. Products over reactants raised to their coefficients. So our product, we have CH3OH. It's got a 1 out front over our CO, right, times our H2 squared. And now we can just plug in these numbers into that equation and solve for our K there. All right? So, K, we're going to have 0.35 over 0.15 times 0.30, and that is squared. And so our answer, when we calculate this all out, we should get 26. All right, plug that in your calculator and see what you got. Remember, no label on equilibrium, so we've just got K is equal to 26. Take a second to soak that in. All right, let's move to the next one and kind of do that. This one we have just a little bit of different work. We've got to do a little different solving, but we'll still be okay. All right, so going back to the beginning, let's start with our red here. Okay, so this time we've got methane, and it's breaking down into ethene, I believe, and H2. All right, we know we have CH4 initially at that, so that's our I. Then we know at equilibrium we have this amount, and we're supposed to find our equilibrium constant. So it's very similar. This time we're just using just a tiny bit different things. So let's see what we got. We have products this time instead of reactants, but it still works the same. Okay, so again, I always like to start with writing the reaction. So we've got 2 CH4 gases, right? We've got our double-sided arrow telling us equilibrium. We've got C2H2, also gas, plus 3H2 gas. So there's our reaction there. We're going to put our ice chart underneath it, ICE, right? Initially, we have 0.115 molar, right? And these other two, since they're products, we're probably going to go with 0. All right. At equilibrium, we know we have 0.035 of our C2H2. Okay. So now looking at this in terms of kind of how we're rolling on, we've got minus 2x, right? Because of this 2, that 2, right? Then we've got plus x, right? And then we have plus 3x because that 3, that 3. Everybody with me so far? So at this point, we know x is equal to 0.035. So let's go ahead and kind of plug that in for our x's. Boop, boop, boop. We'll lose our x's there. And we'll use 0.035 there. And that'll give us our equilibrium concentration. So let's go ahead and take 2 times 0.035 to make sure we're there. And this is going to give us 0.07. Hopefully you can see that. Hopefully I'm not making it too rough there. Maybe if I blow it up a little bit. So we're going to take 0.115 minus 0.07. So our equilibrium concentration of our CH4 is 0.045. Okay, kind of rolling over here. 3 times 0.035 gives me 0.105. Okay, there's that part. Now we want to write our equilibrium constant expression. So K sub C, remember we have products over reactants. So we've got C2H2 concentration times the concentration of H2 to the third over CH4 squared. And now we're just ready to plug those babies in and see what we come up with. So C2H2 at equilibrium is 0.035. We have our H2, 0.105, and that's going to be cubed over 0.045, and that's going to be squared. And now we're ready just to do our math. So 0.035 times 0.105, and that's cubed, so we want to cube it first, right? And then we'll divide that by 0.045, and that one is squared again before we do the division, and we should come up with 0.020. And that's actually 2.0 for a while, but with sig figs, right? There's 3 there and there's 2 there, so our answer contains 2. Remember, no label on K, and we're good, and we're done. See you next time.